Yeah, so now we're going to jump into an exercise on in-place volume, or a range of different exercises. And the way we'll do this is to go through each and one of them, and then I'll assume that you all either click pause on the video and then do the exercise yourself, or just simply try to follow the reasoning and the workflows that I'm doing here in the video, and try to understand it the best you can. So the goals and objective of this exercise is to make calculations with fundamental black oil PVT properties, understand the differences between producing GOR and solution GOR, and then understand the meaning of the so-called geologist BO that we've presented just now. Good stuff. So the first exercise is fairly straightforward. It actually tries to link some of the things we learned earlier with relationship to reservoir fluid classification, and see if we can put that knowledge into practice here by solving this exercise of producing GOR. So we presented the producing GOR in the last lesson, and we will try to remember some of these definitions that we have in order to try to simplify these formulas for these different fluid systems. The first one is dry gas, the second one is wet gas, the third one is gas condensate, and the fourth one is black oil. And PWF is then bottom hole pressure above the saturation pressure. So this is always single phase type of behavior. So at this point, you can stop the screen, and you can try to do the exercise yourself. And if you then press play again, you'll then see the answers. Great. So now I assume that you clicked play, pause and try to do this yourself, and then we'll go through the answers right here. And the solution is given in this particular slide, where simplifying this formula for a dry gas reservoir, we know by definition that no condensate is produced at surface. Hence, both these guys down here will be zero, which gives us essentially a limit where the producing GOR goes to infinity, or where the OGR or CGR, which is the condensate gas ratio, is essentially zero. Okay. For the wet gas case, we know that, okay, there is no surface or there's no reservoir oil phase. So we know that these guys, so we can ignore this guy and this guy, but we know that we're producing a little bit of condensate at surface. So the producing GOR will be VG hat over VO hat G, okay? So this formula right here. And what we see is that this is actually equal to the inverse of the solution CGR. For the gas condensate case, actually, since we per definition said that the gas condensate case was producing at pressures above the saturation pressure, everything is single phase. There is only one phase in the reservoir. That phase is the reservoir gas phase, and we actually remain and get the exact same formula. And we see that the producing GOR is just the inverse of the solution GOR. The last case is the black oil case. That's the only of these four alternatives where we have a reservoir oil phase. So we know that there's no reservoir gas, so we can just remove these two guys right there. And we know we're above since we know we were above the bubble point. And we simply just plug in these two other terms here, which is the surface gas volume from the reservoir oil, and the surface oil volume from the reservoir oil phase, which then leads us to this producing GOR being equal to the solution GOR. Great. From here, we'll take this a step forward, and we'll try to consider three different scenarios, I guess. One being initially, an only oil reservoir oil in situ fluid, and then an only reservoir gas in situ fluid, and then both a reservoir with both phases flowing at the same time. And what's I guess worth mentioning here is that we for a reservoir oil case, as we just mentioned, we know that the producing GOR is equal to the solution GOR when the PWF, so when we are above the saturation pressure, essentially, in terms of pressure. So for unconventional reservoirs, we typically say that the bottom hole pressure has to be above the saturation pressure, while in conventional reservoirs, you typically assign the average reservoir pressure and use that as a baseline. Similarly, for reservoir gas, we know that the producing GOR is equal to 1 over the solution GOR, while when you have two phases in situ, the producing GOR, what you're actually producing, will be somewhere between the solution GOR of your reservoir oil and 1 over the solution CGR for your reservoir gas phase. You know, I guess the different GORs that you'll end up with is a function of rel perms, as a function of saturations, and all these things that is beyond the scope of this course. But we know that at least we know the bounds, and that it will be somewhere between these two ranges. So we've defined these things now, and we would like to do exercise B, where we have a only reservoir oil case, where we have a formation volume factor of 2, solution GOR of 2,000, hydrocarbon pore volume of 20 million reservoir barrels. So this is probably an unconventional well, I guess. And we've done sampling at a GOR that's when the GOR is constant, as given from the drawing ahead of us. And we will try to calculate the original oil in place and the original gas in place and the so-called recovery factor of reservoir oil. Okay. So at this point you can stop and you can try to do the exercise yourself. And then I'll come in and then help with the exercise, I hope. Okay, so now you can unpause and I'll go through how you essentially will solve this exercise. Very, very simply, the original oil in place, as we saw per definition, is just given as the hydrocarbon pore volume from reservoir oil divided by BOI, which in this case gives us 10 million, so 10 to the 6th stock tank barrels, right? When we talk about the original gas in place, we have to simply take this NO number right here and multiply with the solution GOR, right? So we then get 2,000 to the 10 to the 3rd. We multiply that with which is the solution GOR, and we multiply that with the oil in place numbers, which is 10 to the 10.6. Okay, so that should result in, so this is barrels, so just to get the units straight as well, we know the units of this guy right here is scuffs per barrel, which will leave us with 20 BCF of gas. Okay, so the oil production is forecasted to 500,000 barrels, and from this particular well, and we have calculated the hydrocarbon pore volume. So the question is then, what is the recovery factor? And the recovery factor would then from reservoir oil. Okay, and per definition, that's just the cumulative oil production that's forecasted, I guess, in this case, divided by NO, which will give us, in this case, 500,000 divided by 5 million, which is just 5%. And this is probably an example from an unconventional well where the recovery factors are low. Good. Now we've introduced a little bit more complexity. So now we're talking about a gas condensate reservoir, and we have to remember some of the things that we learned from the gas condensate, I guess, lectures or lessons that we've gone through. The first thing that we need to do is to calculate the original gas in place numbers. and the second thing is to calculate the original oil in place numbers, and the third thing is to calculate this BGDI divided by little rs, which is this geologist BOI. Okay, so at this point you can pause, you can try to do the exercise yourself, and when you unpause, I'll walk you through the exercise. At this point, I hope you've unpaused again, such that we can do the exercise together. What I'll probably try to do is to do the number C first, and hopefully that will make sense when I do it. Okay, so to do this, it's because it's just plugging in numbers. I hope 0.0006 reservoir barrels per scuffs. And then we divide that by 75 stock tank barrels, so that the units are correct, per 10 to the 6th scuffs, right? That's what MMCF stands for. Which then allows us to, I guess, move this guy up here. We can do that calculation, and I'll do that quickly on my phone here. So we do 0.006 times divided by 75, which gives us 8 barrels, 8 reservoir barrels, 8 reservoir barrels per stock tank barrel. And as we remember, as a rule of thumb basis, like we know that this number should be typically somewhere either from around 3, 4, 3.5, maybe 4 and upwards, as we saw on the last slide. So that's good. The second thing we mentioned earlier was that, okay, once we have this number, we can apply that at the same way as we've done for an oil reservoir. And here we know that the hydrocarbon pore volume is 20 million reservoir barrels. So we've made it easy for us in that sense. And to calculate the original oil in place, then we simply just take this reservoir, or this fictitious BOI, and we take 20 mmRB and we divide by 8, right? RBs per stock tank barrels. Okay, and if we do that, I have to, my calculation skills in my head is not the best, so I'll do that quickly, and then you get 2.5 million, so 10 to the 6th stock tank barrels. Okay. So sorry if this is a little bit messy, but yeah, so this should be 2.5 million stock tank barrels of condensate. And then we just have the last exercise, which I guess hopefully should be straightforward, which is calculating the original gas in place, which we know is by definition, and as we just learned, this GG value divided by BGD. And plugging that into this formula, we get 20 times to the 6 divided by 0.0006 RB per scuffs. Right, so I'll plug up my phone again to see that I can actually do this by 0.0006. That was a difficult number, so yeah, which leaves us with 33.33 BCF. Okay, so just to summarize a little bit, because this became a little bit messy, we know that A is 33.3 BCF. B is 2.5 million stock tank barrels. And we know that C is 8 reservoir barrels per stock tank barrels. Good stuff. And Now we're going to increase the level of complexity one step more. And that's to do exercise D, where we're actually producing from a two-phase system down in the reservoir. And I'll just have to actually reduce this guy a little bit to get all the numbers. But here we were thinking that we have a reservoir where we know the PVT properties of the reservoir oil phase and the reservoir gas phase, and then we know as well that at this particular point in time we're producing 20% of the reservoir oil and we're producing 80% of the reservoir gas phase. And then our job is to define how or what is actually the producing GOR. Okay, so just for the sake of this exercise, or the first thing that you can do is try to do the exercise yourself by clicking pause, and when you're back, we will do this exercise together. So now I hope that you've clicked pause and tried the best you can yourself, and then we'll try to do this together. And what's always good to do while we're doing these kind of exercises is to create or just make up some kind of basis in terms of doing that counting. So just for the sake of this exercise, what I'll do is that I'll just choose a reservoir volume of 10 reservoir barrels. Okay, just so we've done that. So this is reservoir barrels. I know that from this particular, and I'll do probably something like this, where I'll account for the reservoir oil right here and the reservoir gas right here. So we've chosen a basis of 10 barrels per, or 10 reservoir barrels. From this particular information, we know that 20% of that is reservoir oil. So we know we have 2 of the barrels that are flowing is reservoir oil, while 8 of them are reservoir gas. Okay? Then we learned in this course that to then translate reservoir volumes to stock tank, we need to apply a formation volume factor. And a formation volume factor for oil is the BO, while a formation volume factor for gas condensate is this BGD over little rs term that we learned, which is given right here. So if we apply the BO and convert, this particular step, just apply a formation volume factor, then we know that 2 reservoir barrels will translate based on this. If we divide this number by 2 reservoir barrels per stock tank barrels, will result in 1 stock tank barrel. Agreed? So here we applied the BO there. If we do the same with the reservoir gas phase and we apply the BGD over little rs, then we here we'll get 8 reservoir barrels divided by 8 reservoir barrels per stock tank barrel, which will also give us 1 stock tank barrel. Okay, and then that's the first step, or I guess the second step, and this was the first step. The third thing we need to do is to also account for, okay, how much condensate or how much gas is actually coming out of solution, and how much for both the reservoir phase that we're producing and the both of the reservoir phases. Sorry. So we first do this simple calculation, and we know that per barrel will produce 2,000 scuffs. That's given by the RS. So apply the RS, or for the gas phase, it will be 1 over the little rs to get it to be scuffs per barrel. On the gas side, what I'll need to do is to make sure that I have this guy right there, 1 divided by 75 times, yeah, so this, so 1 over little rs is given to be 13,000 scuffs per barrel. Okay, so we then know that the one stock tank barrel right here will then, if we apply an RS, or the inverse of that, would be give us 13,000 scuffs per barrel. Okay, so we've done all the math now, and just to I guess sum up a little bit, just to make sure that we've done this correctly, and I'll try to just give ourselves a little bit more real estate right here, just to sum up what we've actually done. So just to make sure that we have everything we need, we know that the RP is defined as the surface gas from the reservoir oil plus the surface gas from the reservoir gas phase over the reservoir oil phase from the reservoir oil, or the surface oil phase from the reservoir oil, and the surface oil phase from the reservoir gas. Okay. Here we know that the surface gas from reservoir oil was 2,000 scuffs. We know that the surface gas from reservoir gas was 13,000. And we know that the reservoir oil, or the surface oil from reservoir oil, was 1. And we know the surface condensate from reservoir gas was 1. This gives us a producing GOR that's equal to 2,000 plus 1,300 and 333 divided by 2 stock tank barrels. Yeah. And then if I just multiply that, okay, let's see here, and I divide by 2, the final answer is a producing GOR of around 7,666 scuffs per barrel. So that's the final answer. Good stuff. I guess in general, what we actually know is not necessarily the saturations of what is flowing actually on a daily basis, like as we did in the last exercise, but actually most typically what we know as engineers is the producing GOR. And that actually allows us to then back calculate the saturations at reservoir conditions and pressures and whatnot at any given day and any point in time by knowing the RP. So we can actually back engineer the problem that we just had to actually quantify these saturations with time. So the exercise D that I'll allow you to try to do now by yourself is to assume that we have a case like what we see behind us here, and then we know RP, and here for the sake of just example, we can say that the RP is let's just say RP is 10,000 scuffs per barrel. How can we use this RP information right here and these properties right here and everything else that we learned to back calculate the saturations on a relative basis of what's flowing that particular day down in the reservoir. So I'll let you guys do the exercise right now, and when you all are back, we will go through this a little bit quickly how that can be done. Good. So now I hope you at least tried to do it, and if you haven't been able to do it, that's also fine. Just to make sure that the reason why we are doing these things is just to try to convey a lot of these key concepts related to black gold PVT and to be able to deal and think with two phases down in the reservoir. And I've cheated a little bit because I don't want to spend too much time on this, but the way you would go about solving this exercise is just to always remember the definitions. The definitions are always key and they will not change. And once you start to think in terms of this nomenclature right here, and remember the different definitions of formation volume factors that we've learned, which is BO and BGD, and then also the solution GOR and the little RS. Once you start to remember those different definitions, which we have given here, you can then use this information and everything that you learned and try to step by step try to derive an equation for essentially what's oil and gas saturation. So this you can see as a gas saturation right here, and this is an oil saturation. That's essentially what it is. If you ignore water. So in a little bit three-step approach, there's several ways to do this, but one way is to, okay, we know producing GOR, so let's define a property for that, and then we have to provide the definition of that, and then we plug in the different PVT related properties into this equation right here. So we take all these guys right here and we see where they fit into this equation. Because what is a saturation? Well, a saturation is simply the relative volume of oil, right? So that will be SO plus SG. So in terms of volume, it will be something like this, right? So we know the definitions of that, and we would like to try to isolate, based on these other known factors, these different terms. So if you do some of the algebra, you will be able to take the RP, translate into a range of reservoir volumes, information volume factors, and GORs, and isolate this particular ratio right here. And all of these properties here will be known, okay? So we'll have, in this particular case, RP, and as the exercise was given as well, we also had all the PVT properties, so all of these ones are known. This is the only unknown, and we can also just reorder the gas saturation equation, for instance, to give us something where we can plug in this particular value. So once we've calculated this at step 1, we can then calculate this at step 2, and then we can calculate the SO by using this formula right here, where SO is essentially equal to 1 minus SG, which is the third step. Then you should be done. And to be honest, I can't remember the number, but the most important thing is that you know that you can back calculate these different properties. And on this particular sheet, there's also given some formulas and definitions that can help you, or just a summary essentially of all the slides here that can help you further.